The most prominent part of NASA's James Webb Space Telescope is its giant, gold primary mirror. Its mission is to see the faintest light from the most distant objects in the universe, which means capturing light that has been traveling for over 13.5 billion years. Catching this faint glow requires an enormous mirror, 6.5 meters across. Webb's is the largest ever to fly in space. The problem is that the mirror is far larger than the rocket fairing built to carry it. But this presented a huge challenge. This light from the early universe has been stretched into the infrared spectrum, making it invisible to us. So, the mirror had to be segmented and folded for launch. This means it has to be unfolded and then focused with incredible precision, all while it's a million miles away in deep space. The solution begins with the material the mirrors are made of, a rare metal called beryllium. This chemical element was chosen because it's both very strong and very lightweight. Finally, the mirror segments were coated with a microscopically thin layer of pure gold, less than 100 nanometers thick. This is because gold is excellent at reflecting infrared light, capturing over 99% of the photons that hit it. But, most importantly, it virtually stops changing its shape when it gets really, really cold. These are tiny motors that can move each mirror precisely in every direction and can even modify each segment's shape ever so slightly. This is critical because the telescope has to operate at minus 233 degrees Celsius. That's colder than the surface of Pluto. Any heat from the telescope itself would blind its sensitive infrared instrument. They pointed the telescope at a single bright star, which at first produced 18 separate, blurry images. It has two wings on the side that folded back, allowing the whole telescope to fit inside its rocket for launch. Starting from mines in Utah, the beryllium was fused into disks, which were then machined and polished. An interesting fact about this process is that all of the polishing was done at room temperature. Because beryllium changes shape with temperature, the mirrors were manufactured to precisely the wrong prescription, so that they would have precisely the right shape at their frigid operating temperatures. This combination of beryllium and gold created the perfect mirror segments, but to solve the size problem, the primary mirror was designed in 3 sections. But after unfolding, how do you get 80 in separate segments to act as a single, perfect mirror? Behind each of the 18 mirror segments is an actuator system. After the telescope unfolded in space, the science team began the alignment process. This process allows all 18 segments to form a single, seamless primary mirror. The light it gathers is then sent on a path. The concave primary mirror reflects it to the secondary convex mirror, which bounces it back to a tertiary mirror, and then, finally, to a fine steering mirror. This directs the light to the science instrument. This setup is technically known as a 3-mirror. This kind of design enables a wider field of view and minimizes optical distortion. After the Webb team aligned those extraordinary mirrors, a new scientific era began, allowing us to look further back in time than ever before.